Our next shuffle is again an alternate Klondike, but this time we will stack the final two piles right on left. Okay, so let's go ahead and demonstrate this shuffle using our ordered packet. So we have 1 through 8. So we're going to perform our shuffle and then take a look at the new ordering of the cards. Okay, alternate Klondike. Remember, this is where you take the bottom and top card off as 1, set the first pair down on the left, bottom and top card off as 1, set that down into a second pair on the right. Top and bottom is 1, and then there's only 2 cards remain. So you just do this left, right, instead of a regular Klondike shuffle where you're stacking them onto a single pile and building it up one level at a time. Now, this time we're going to stack the right pile on top of the left, okay? And as you would guess, this is going to lead to a different order than stacking left on right. So what is the new ordering that we get? We get 4, 5, 2, 7, 3, 6, 1, 8. Writing this in Cauchy's 2-line notation, we obtain the following. Top row is always 1 through 8. Bottom row is 4, 5, 2, 7, 3, 6, 1, 8. And we can convert this to cycle notation as follows. Note that 1 goes to 4, so we have an arrow from 1 to 4. 4 goes to 7, so we have an arrow from 4 to 7. And then 7 returns to 1, so it cycles around, completing a 3 cycle. 2, what happens with 2? 2 goes to 5, so we have an arrow from 2 to 5. 5 goes to 3, so there you go. And then 3 returns back to 2, so it cycles around, giving us a second 3 cycle. 6 goes to 6, so it's a fixed point. So whatever begins in position 6 will return to position 6 once this shuffle is completed. The same thing for position 8. 8 goes to 8. Whatever begins in position 8 will end in position 8. Color coding the digits, we obtain the following. Recall that the 2 distinct sets of position values of importance to us in the study of Bessey sequences are the following. The set consisting of position values 1, 4, 6, 7, and they are color-coded black, and its complement, the position values 2, 3, 5, 8, and we color-code those red. And after the shuffle is complete, one of 2 things will happen. Either the Bessey sequence is preserved or it is inverted. So here we see that black 1 goes to black 4, which goes to black 7, which wraps around to black 1. Red 2 goes to 5, which goes to red 3, which wraps around to red 2. Black 6 goes to itself, and red 8 goes to itself. So we see here each value gets sent to a value of the same color. And when that happens, we say that the Bessey structure of the sequence has been preserved. So there's no inversion of the sequence in this case. And we should be able to readily confirm that by working with our Bessey sequence 1001, 0110 and performing this shuffle. So what should happen is it should return this packet back to its original form as a Bessey sequence. So let's go ahead and perform the shuffle. Remember, top and bottom come off as 1. Set that down on the left. Top and bottom off as 1. Set down on the right. Top and bottom on the left. Last 2 on the right. We're stacking right pile on top of the left. Okay? So we're expecting to see the same 1001, 0110, which we do. And all of the cards labeled with 0s and 1s have actually moved to new locations except for The 1 in position 6 stays in position 6, and the 0 down here in position 8 stays in position 8. Those are fixed points. The other values are being permuted among their digit values of either 0 or 1. Taking a look at the shuffle diagram for this one, so top row on the right, we can see our fixed points of 6 down here and 8 up here, and then we know that 1 goes to 4, 4 goes to 7, 7 returns back to 1. So if we begin at 1, there will be an arrow from 1 down to 4, from 4 up to 7, and then from 7 back to 1. So that completes a 3 cycle. We also say that the values 1, 4, 7 are members of the same orbit. Those values just move around among themselves according to the direction of the arrows in our diagram. Similarly, 2 goes to 5, 5 goes to 3, 3 goes back to 2. So if we come down here to 2, there's an arrow from 2 down to 5, from 5 up to 3, and then 3 straight up to 2. That completes our second 3 cycle. And those 3 values constitute their own orbit as well. I guess I should point out that value 6 here constitutes its own orbit, meaning it doesn't go anywhere, and the same thing for 8. It's an orbit that consists of just one value, or one number. And as indicated up here, inversion does not occur. And as mentioned earlier for the previous shuffle, I have some special notes here, top left, pointing out how special the alternate Klondike is, because it's one of very few shuffles that will convert a 2-cycle structure to a mirrored structure, to an AMP structure, and then back to a 2-cycle structure. And I need to emphasize that when we refer to 2-cycle structures here, we're referring to the 2-cycle structures studied in the Hidden Structures online course. And they are always written with a capital C for 2-cycle, whereas when we talk about cycle notation and perhaps a 2-cycle or a transposition, we always use a lowercase c to keep those two concepts separate. So this will make sense to those who have looked into the Hidden Structures online course. And this diagram is true provided that we have 4n cards or 4n objects.